Heard a lot about SKA, heard a lot about where it's going to be. This is a Google Earth map. You can see sometimes described as being near Geraldton. It's really not very near Geraldton. It's quite a long way away from anywhere. The SKA has a number of precursors. There's Meerkat in South Africa, and there's ASCAP and MWA here. So MWA is a bit more like an open source project in that there's a whole bunch of different institutions contributing money and people. It's a bit like an open source project and a bit like herding cats. Everybody has their own little pot of money. Everybody wants to spend somebody else's pot of money and not theirs. Everybody has their own little internal management structure that decides what to do. And until quite recently, there was no sort of overall manager and overall pot of money to actually sort of make sure everybody was heading in the right direction. And the programming acts a bit like that too. You get people coming on board, working for a while, and then all of a sudden they're not getting paid to do something that they were doing for the last few years, so they sort of move on to other projects. ASCAP is being funded and built by CSIRO. So it's bureaucratic, slow-moving, but on the other hand, they move in the same direction, and you know they're pretty much going to get where they're going. They just might take a little bit longer. ASCAP has got the bigger budget. MWA has had the flexibility. In particular, MWA got on the ground quicker because the indigenous usage agreement wasn't signed for the actual observatory, the actual site. So ASCAP, which required digging foundations, digging trenches, digging lots of concrete, moving earth, making buildings, they couldn't get started. Whereas MWA is literally just pieces of mesh resting on the ground, so we could come to a much more beneficial agreement much quicker, and without as much legality to just say, look, if you let us in there, anything we put on the ground we'll take away if the eventual agreement isn't settled. So we could actually get on the ground and start doing initial observations very quickly. Neither of these projects is funded by the SKA, in quotes. The SKA is an international project with money that's currently only funding people in Manchester and a few bits and pieces to do sort of big overarching SKA stuff. ASCAP and MWA have their own budgets and their own funding sources. SKA itself is being built on Buladi Station, which is sitting in the middle of Murchison Shire. It's a pastoral lease. The MWA itself, the original aims were to use the hydrogen spin flip line, which is what you look at when you go in an fMRI machine, hydrogen spin flip in water molecules in your body. And they're looking at hydrogen spin flip back in the early days of the universe when the neutral hydrogen gas was first becoming ionized. That's redshifted down from gigahertz down to a few hundred megahertz. You can also look at solar eruptions in real time. We get tens of pixels in radio across the surface of the sun. So we can actually look at the surface of the sun in radio, and we can look at these solar flares, coronal mass ejections as they travel through the solar system and come towards the Earth. And we can look at background radio sources to look at magnetic fields in the solar system in 3D. And we can do a whole heap of stuff that wasn't anticipated because nobody's ever looked at the sky in these wavelengths before. So there's sort of known and unknown radio sources, both fixed and variable. So this is a breakaway. It's a sort of red granite, typical of the sort of Kalamunda Hills. It's 60 to 70 million years old, this surface. So this was the ground level on top of these breakaways about 60 or 70 million years ago. And it's been being eroded away ever since. So these breakaways are crumbling. They're turning into red dust. The red dust is being blown away. The flatter area here, it's about a few 10 meters or so lower down, is grey granite with a very thin layer of red dust on top. And this is the area that was picked for the Radio Astronomy Observatory because nobody wants it. It's a thin layer of red dust on top of rock-hard grey granite, and there's been exhaustive surveys that have decided that there's absolutely no useful minerals there. Nothing grows in it higher than about chest high because the ground is too shallow. So the MWA is a whole bunch of these dipoles. In pictures like this, they look like they're menacing multi-meter towers, but they're actually knee-high and quite sharp. I've taken out the knees on a few pair of trousers. The idea is that you have a group of 16 of these dipoles. Each of these dipoles has an X polarization that runs north-south, a Y polarization that runs east-west. So it's two separate antennas inside each of these spider objects. Two little amplifiers in here that amplify the X and the Y separately. And they're sitting on top of a 5 by 5 meter square of steel mesh. And this forms a steerable radio telescope. The way it's done is that you selectively delay the signals from each of these antennas. If you want to be sensitive to signals that are coming from straight overhead, you add up all of the analog signals with no delay in between them. So you add them up, they all have identical cable lengths, they all run to this box here called a beamformer. They're all added with zero delay in between these elements. So that means any source coming from the sky that hits all of these antennae at precisely the same time, because it's coming from straight overhead, the signals will sum together and reinforce. If an object is coming in from some direction like on the side, it'll hit this antenna first, then these ones, then these ones, then these ones. And if that's summed together with a zero delay in between the elements, the signals won't reinforce as well. So it'll be very sensitive to objects coming from, signals coming from straight up, less sensitive to signals coming from the side. If you want to point the dish in a different, point the tile in a different direction, all you do is change the delays. So you introduce different delays for each of these dipoles, and you can selectively become more or less sensitive to different directions. Basically a phased array antenna, which was inside pretty much every cell phone now. 8 of these tiles, which are, this beamformer puts out analog coax that runs across the desert with a purely analog signal from this single steerable antenna, runs across the desert. 8 of them go into a box called a receiver. That's where they're digitized. There's a bunch of digital electronics after the A to D converter that does all of the processing. They're inside shielded boxes, so they don't put radio frequency interference in the outside world. And there's 16 of these receivers scattered across the desert, each of which is connected to 8 tiles. And the only thing that come out of that receiver is fibre, because fibre doesn't transmit RFI. We can't run Cat5. So a bunch of these receivers are connected to a central hub, and at the central hub you do all of the number crunching. So this is a prototype. You can see a couple of cars here for scale. This is a shielded box that arrived on wheels. It's a sort of a trailer. This is another thrifty hire trailer or something like that. And 32 of these steel mesh squares with 16 dipoles in each one. So we built a prototype, and the prototype, I think that they actually physically dragged the mesh around and made these tiles in late 2007, and they were running it from about 2007 through to about November 2011. I think it was November, October 2011, something like that. So that was the test phase with these 32 tiles.
You're just recovering energy, right?
Yep. The demountable building has 3 air conditioners. The one at this end was set to 45 degrees, the one at this end was set to 15 degrees, and they fought each other and consumed more power. Everybody clustered down the 15-degree end. Some of them ventured as far as the 20, 25-degree end, and nobody wanted to sit down this end. So these are the tiles. These are slightly different dipoles that are a bit taller and narrower than the ones we eventually settled on. And this is a tile out in the bush. This beamformer here has the 32 wires, 16 of these dipoles, each of which has X and Y. They're handled separately. So 32 of these wires go into this box. And this is where the delays are done. So the communication with this box, there's 2 wires going to the box. This is an old one. The new ones have 2 pieces of coax going to the box. That coax carries an X signal back, a Y signal back in analog from 80 to 300 megahertz. It carries 48 volt power to run all of these amplifiers here. Let's step down from 48 volts for the long run back to the receiver, down to 5 volts for these amplifiers. And it also has a very low frequency digital communication to set the pointing of the tile to what these values. And the pointing is done using delay lines. This is the inside of a beamformer. That's 16 dipoles for X on the top, 16 dipoles for Y on the bottom, different boards. And the delays are done with little loops of wire. So this is the shortest delay, about 1 centimeter, and 2 analog switches that will either send the signal straight through or around this little loop of wire. The next up is about 2 centimeters, so 2 little switches will send it around the little loop of wire or straight through. So on for each of 5 loops of wire, and the longest one is on the far side of the board, so it goes backwards and forward quite a few times. So you can delay the signal by this much copper, or this much copper, or 31 steps in between. So it's very, very simple analog delays. And then after all of the signals have been delayed by the right amount, they're all the same if you want to look straight up, or different if you want to look sideways, they're all summed together and dumped out on the piece of coax. So this box here is the bit that steers the telescope. So we need to send this the correct stream of bits to turn each of these switches on and off and set it to the right state so that we're pointing the array in the right direction. So if you want to do interferometry, if you want to use a whole bunch of these things and connect them together, you could in principle do that to the tiles. You could say, we've got a tile over here, we've got a tile over here, both of them are pointing this way by analog delays in all of the wires. So we could do the same thing with the tiles. We could say, take the signal from this tile and delay it by a certain amount depending on how long the cable is back to this central location. Take the signal from that tile, delay it by a certain amount, and do it all in analog. And that would let us steer the entire array, just the same as we steer a tile. The problem is, the wires going out to the tiles are like a kilometre long in some cases, between the physical coax and the fibre taking it back to the main building. So there's lots of physically large pieces of wire. Thermal expansion changes the length of the wires quite considerably. The two tiles will be different places, they're different temperatures, the wires would expand by different amounts. So it's physically very difficult to do to get delays to that accuracy, to measure and account for delays of like a few millimeters in a kilometre of wire. And the other problem is that it gives you a single pixel. You do all of this and you point the entire telescope with 128 tiles all in the same direction. You get 1 pixel's worth of data. So what you do is you do it in software. So instead of getting the brightness at one tiny position on the sky, and to move it, you change all the delay times and make another measurement. What you do is you measure and record the data coming from one tile, you record the data coming from another tile, you keep the time information, and you know when this data was received, when that data was received, and then you do all of the variable delay sums digitally in the computer. And that way, you can keep doing this repeatedly, and basically you do it in parallel, so you're adding all of these signals together at every possible delay. So you build a picture of the sky with every possible choice of delay for all of your tiles to get a complete image. And that hand-waving explanation is about as far as I can go. If you want anything more, talk to Steve, because he's the guy that actually does all of this processing. So this is the early prototype. All of the signals from all 32 tiles came into this box. 4 receivers were inside the box, and each of the receivers has some bits you need to control. You've got 16 wires coming in, X and Y for each of 8 tiles. They go into what's called the analog tile interface module, which physically connects it, has things like lightning isolation, stuff like that. Then you've got 2 boxes, each of which has 8 inputs, and they do filtering, analog filtering. So you make sure that you've got 300 megahertz bandpass, you have some gain control so you don't saturate your A to D converter and you're not looking at noise if the signal's low. So these 2 boards here have an I2C control for gain on each of the channels. Then you've got your A to D converters. You have 2 boards full of FPGAs, 1 FPGA for each of these 4 channels, and a dual channel A to D converter for each of these 4 channels. And this digitizes at 655.36 megahertz, which is a nice round number to anybody that knows binary. And it also has a FPGA doing filtering. So there's a fast Fourier transform in each of these signals that takes it from down to 24 arbitrary channels. Sorry, there are 256 channels coming out of the A to D, coming out of the fast Fourier transform here, and then 8 of those channels. 24 of those channels go to this box here, which allows you to choose which 24 of the 256 channels you're actually going to send out down these 3 fibers. And you've got 3 optical fibers, they're transmit only, custom protocol, 3 2.5 gigabit fibers, each of which has 8 channels going out, which gives you the 24. So this board here, and this board here all have USB interfaces to define your A to D converter characteristics, how you're going to do the digitization, how you're going to do the filtering. You can access information like how many counts in the last second have gone over a certain threshold as far as saturating the A to Ds. You get information about monitoring out. Your AGFO here is where you choose which 24 of the 256 channels are going to go out to the outside world. You've got an incoming clock. You've got a 655 megahertz clock, and every 655 millionth pulse is longer, I think. And that longer pulse gives you a 1 second tick. And you've got a single board computer in here. It's a little Vortex 86 CPU. It's a board about this big. A whole bunch of digital I/O to communicate with these things here, turn power supplies on and off and things like that. I2C buses for temperature monitoring, for controlling gain, for monitoring voltages and currents. And you've got USB comms with these 3 devices here. And this little box here runs Linux and has its own sort of Cat5 100 megabit Ethernet fiber pair. So you've got 3 outgoing fibers that don't run TCP, they just dump data continuously. 1 incoming fiber that only has your 655 megahertz clock, and 1 fiber pair for Ethernet communications. Any questions about that before I go any further? Yep.
You mentioned about temperature inside of the receivers.
Yep.
Did you mention about how you control the temperature?
I'll get to that in a bit. The 32T receiver was in a nice air-conditioned rack, so we didn't really have to worry about that too much. The newer ones are air-conditioned. I'll get into that. It's actually the next slide.
What's the reason for using analog delay with like loop supply rather than digital?
Because if you did it digitally, you'd have to digitize 32 times as many signals.
Right.
And you need quite a significant amount of computing at each tile.
It's just a compute.
Yeah. Compute, and if you have that amount of computing, it needs to be RFI screened. It'll generate heat, which means you need air conditioning. If you do it entirely in analog, those boxes aren't air conditioned at all. They're just sitting out in the dirt and they're at 60 degrees. The original prototyping hut was quite narrow. It had just enough room for 2 racks, and if you could squeeze to the left or the right of one of those racks if you were skinny, and just enough room to sort of stand behind the rack and get at it. We have here the 4 prototype receivers, 1, 2, 3, 4, each of which has 32 tiles going into it. We've got some storage down here, and we've got a box here doing processing. So this is all quite ancient now. This is the system as it existed in about 2009. This is Mike Watterson from Curtin peering into one of those receivers. This was the first of the Linux boxes. Now it's not in one of these nice little blue boxes. It's sort of a single board embedded in the rack. You have one of the ADFBs. This is a box that takes 8 digital inputs and digitizes them and does a fast Fourier transform. The other one is over here, and this box in the middle is the AGFO, the bit that does the capture 24 of the 256 channels from the backplane and dump them out these fibers that are sitting on the top. Power supplies, and that's the antenna interface bit. The new ones sit out in the field. So instead of a rack in a cage that has 4 of these receivers in, this is 1 receiver, and there are now 16 of these boxes sitting out in the field. This side here is the air conditioner. And this box here is the actual bit with the digital electronics crate in, and there's a vast quantity of RFI shielding. This is all completely shielded. It's all made of high conductivity tongues and grooves and things for the lids. There's 10,000 screws to open up some of the cage type stuff in here. It's quite an unpleasant piece of kit to work on. The air conditioner sits in here, and you open that box up and it looks like you're looking at the inside of a bar fridge. It's nothing particularly high tech. So this is the receiver itself. This rack module here. For some reason, they decided to go for something that is almost but not quite a 19-inch rack. It's like 18.7 or 18.5 or something. God knows why. So we have a not 19-inch rack with a module here that has a CPU. module here with a power supply and CPU, module here for 180FB, then you have the, no, sorry, that's 1AFB. Oh, this is the ASC. So power supply and CPU, analog signal conditioning, so that's the filters and variable gain. 80FB does the digitizing, then you have the AGFO in the middle, then you have another 80FB, another analog signal, and, sorry, that's power supplies, this is computer.
It's got the switch on the end.
Yes, that's a computer and that's the Ethernet switch. And this is the some of the bits that actually talk to the tiles coming out here. So the 80FB, that box inside a receiver, has the first stage of filtering. It's called the coarse polyphase filter bank, and that carries out a Fourier transform. And that splits the data from each of the 8 tiles into your 256 channels. And each of those channels is 1.28 megahertz wide. You might notice a theme here with powers of 2. Each of those 3 2.5 gigabit output fibers carries 8 of those 24 channels. So we select those for observing. And that goes to the shielded correlator room. And that's a funky building that CSIRO built that's completely shielded. And that goes into what's called a fine PFB card, which is another board full of FPGAs that does another fast Fourier transform. So we've got a rack, or a couple of racks full of custom-built cards that split each of those 24 channels into 128 fine channels, and those fine channels are 10 kilohertz wide. So this is the fine PFB. So we have 1, 2 of the fine PFB cards, and we have another card in the middle that does control and management of these 2 cards. Each of these cards has 12 fiber inputs. So there are 3 fibers coming out of the receivers. So each of these cards carries the complete data output from 4 receivers. So we have 4 receivers being processed here, another 4 receivers being processed here, and on the other side of the next rack we have another 4 receivers and another 4 receivers and another one of these boxes. So this starts to do what's called a corner turn. When we're trying to process the data, we can't physically get all of the data from the entire array into one computer. But to do interferometry, you need all of the signals from all of the tiles to do the variable delays. So what we need to do is, instead of having all of the data from one receiver on these 3 tiles here that carries all 24 channels and goes into this board here, we need to try and split it up by frequency. So each of these cards takes 4 receivers worth of data, all 24 channels from 4 receivers, and processes it, and it has some output fibers. And those output fibers are here, and they split the data by frequency instead of by receiver. So for the first time, we're starting to have multiple receivers combined with a smaller number of channels. So these output fibers go to a rack of 16 Cisco servers. These are called the VCS boxes. So we have 16 of these boxes, each of which has a few fibers coming in from the fine PFB, and it carries some of the frequencies from more than one receiver. I can't remember the exact numbers. Steve would have to. Do you remember how many receivers each Cisco box handles?
Well, each Cisco box gets 1/8 of the frequency channels from 1/4 of the array.
Okay, so we've started to split it up. Instead of being all of the channels from one receiver coming along one fiber, we started to split it up. The next stage, we split it up to 1 box per channel. Oh, this is one entire rack. So we have 1 fine PFB and 8 of these Cisco boxes that handles half of the array. So these things here come from 8 of the 16 receivers, and these Cisco boxes handle those 16 receivers. And each of these Cisco boxes is full of disks. These are empty caddies because it's an old photo, but they're now full of disks. And these 16 Cisco boxes, this rack and the one like it, have about a 53 terabyte very, very high-speed storage. So these are filled with 900 gig and 300 gig, 10,000 RPM ultra-fast drives. So in what, RAID 5? Yeah, so they're very, very high speed, capable of storing transient data where you want to look at something that changes state very, very frequently, you know, at very high-speed oscillations, like pulsars and transients and stuff like that. By the time it gets through the rest of the processing stage, you're looking at 1 second integrations, maybe 2 seconds, maybe half a second if you go real quickly. So you can't look at anything that changes in less than like a half a second or a 1 second time scale unless you record the data here. Then it goes to the GPU boxes, and each of these boxes, there's 24 of them, 24 boxes, each of which handles the entire array, but only for one frequency channel. These 24 boxes have 2 Nvidia Tesla cards in them, and they run Steve's code, so I'm not going to talk any more about it. It's CUDA stuff that I don't understand. So this is where the racks sit. That's Dave Emmerich and Brian Cross sitting in the CSIRO corollary room. All of our racks are behind them. These ones are all empty. These ones from about here backwards to the other end of the room are all full. And it's an unusual place to work because it's hermetically sealed. Like any server room, we've got a fire control system, but it's also behind 2 complete layers of Faraday cage. So the water coming in to cool these racks has to pass through metal mesh, lots of big sections of metal mesh to stop electrical signals leaking out through the water. All of the mains coming in is massively filtered. Fibre comes in large numbers. The building air conditioning system sometimes fails, so there's oxygen and carbon dioxide temperature, carbon dioxide sensors in all of the rooms. And if the alarm starts going, you need to leave quite quickly. There's air locks, well, not air locks, but RFI locks. So this is a massive copper and brass door. There's another one here, and there's an interlock system that the director sort of stomps on you if you open up both doors at the same time. So this is some of those 128 tiles. So the wires running across the desert. These are dragged by hand, trudging through the desert, towing twin 10-core RG6 or LMR400 cable for a kilometre or so to these tiles. And there's a lot of computers, as you might expect. We have a gateway computer that runs NAT and DNS and DHCP and Nagios to monitor the health of all the machines. We have a main MNC server, which runs a Postgres server that's the core of the scheduling system. A few daemons to communicate with the receivers and receiver communication. We've got 16 of these single board Linux boxes that actually talk to the hardware on a receiver. We've got 2 what are called odd jobs, and each of them manages one of those fine PFB shelves, communicates via UDP with a control card, and sets it up and programs the firmware on the cards at boot and stuff like that. 16 of these Cisco voltage capture servers that are all PXE booting using an NFS image. And they've got this 53 terabytes of RAID away for high-speed captures. 24 of these IBM servers, each of which has got 2 of these Tesla cards. That runs a software correlator. We've got 2 VMsphere servers running a grand total of 3 VMs. We don't really use the VMs as much as we should. And we've got 2 local data archive servers. IBM, I think, I'm not quite sure what the archive servers are, with about 80 terabytes of local storage. And we have a dedicated 10 gigabit link for data transfer all the way back to the Palsy Center in Perth. So we've got our own 10 gigabit fibre lit to carry data back to Perth. And that 80 terabytes is for when the fibre's down, provide a little bit of a buffer. The data, once it gets to Perth, goes into the Palsy Center, goes into some local storage first, and it goes into the main Palsy large-scale archive. We've got 9 petabytes allocated in the tape system to us for 2 years' worth of operations. So far, we've taken 773 hours of data. That's from July through to when we closed down for Christmas. And that's about 900 terabytes and about 1.1 million files. So we haven't made much of a dent in that 9 petabytes. And it's also mirrored to MIT. There's the National NGAS. What does NGAS stand for? Yeah, it's code to mirror and allow the scientists to grab data and do stuff like that. So the software running is all sort of hand-coded. It's not something you can really use off-the-shelf stuff for. We've got daemons to handle USB, I2C, and digital I/O comms on the single-board computers to do temperature monitoring, to set up the configuration of the hardware. And that's a mixture of C and Python. We've got the MNC daemons running on the MNC server to talk to the receivers. The scheduling stuff runs Java, and the receiver status monitoring and logging is all in Python. We've got correlator control, which manages all the processes on the VCS boxes and the GPU boxes, starts them all up, shuts them all down, looks at status, stuff like that. and that communicates over Thrift, and it's all written in Python. We've got the data processing software that's Steve's baby in CUDA and C++. And we've got the science data archiving, which is NGAS in Python. That runs on both the machines on site and on the sort of Posy Center computers. And you can see it's a bit of a mixture of languages. It's because we get people joining the project, working for a while, and then leaving. And depending on what sort of person it is, if it's a PhD student, you get a lot of their time for the first year or two, and then they realize they need to actually write their thesis, and they sort of peter down slowly. You can prod them into telling you how something works for a year or two after they stop actually developing and doing sort of lots of work. Then you have the postdocs that sort of come and go in between a line of code. They go from being there and working to being gone. And you have the sort of faculty that they sort of hang around for a really long time. Sometimes the university stops paying them to do what you want them to do, so they kind of peter down a bit, but they're a lot more flexible. And everybody comes to the party and contributes what they want. So if somebody comes along and says, well, I know Fortran and Haskell, what can I do? You kind of say, nothing, please, go away. Somebody comes along and says, I know Python and I'm really keen. They say, yes, yes. We haven't actually had anybody say Haskell. Okay. We haven't actually had anybody volunteer Haskell. The Java stuff is done because the people that were working on it at the time knew Java and liked it and didn't know Python, so we're kind of stuck with Java and Python for the code that doesn't need to be really resource intensive. We had a bit of PHP, we had a bit of Ruby, we had bits and pieces, but we're kind of merging towards Python for the non-data intensive stuff. I'm at the moment replacing all of the C on the receiver with Python, which is a slow and painful process. Observation scheduling, there's a command line interface for adding observations, and that's done mostly because most of these observations need to be scripted. So you generally want to schedule a whole bunch of observations that are kind of similar. You might want to tile across the sky, you might want to follow something for a while, you might want to look at a whole bunch of things that are similar. So command line interface is kind of nice because people can write their own little Python scripts for running this and scheduling observations. Each observation has a defined start and finish time along with some other metadata. And then that observation record points to one or more RF streams. And an RF stream defines a configuration for a particular set of tiles. So you can have different parts of the telescope doing different things. So an observation contains a whole bunch of RF streams. Each RF stream defines a configuration for one tile or 128 tiles. The name of the set of tiles that an RF stream refers to is actually instantiated when the observation starts. So you can define an observation to be on all working tiles, for example. You can schedule that observation on Monday, and then you might run an engineering test on Tuesday that says, well, this tile isn't working, I'm going to remove it from the set of working tiles. When the observation happens, it uses the current value for that set of tiles. So you can have different sets of tiles. You might find that some tiles are marginal, so one science group is happy to use a marginal tile to get extra signal. Another science group wants to exclude it. So we're going to have different tile sets that people work with. So these scheduled observations are written to a set of database tables. They define the future configuration of the telescope. And then there's a single daemon that looks at that future configuration and says, well, the time is now. In about 1.5 seconds, the configuration needs to be set up for this observation. So I'm going to send all of this data to the receiver. I'm going to tell the receiver when that observation starts. At the instant the observation starts, the receiver has changed configuration and is ready to start sending data. So we have, well, not particularly interesting database tables that define the schedule. Inter-process communications, again, it's a bit of a mixture. The original inter-process communication was between the OBS controller and the receivers to send the configuration, and that was XML over TCP. And it's a bit of a horrifying custom protocol, and that'll be phased out eventually, but it's kind of hard to do, mostly because I don't grok Java. PostgreSQL, this is a bit of a hack, but everybody knows how to write to a database table. So you had one process writing status data to Postgres and another process reading it. And it works really well, but it doesn't scale very well unless you do it very, very carefully. So we're phasing that out and replacing it with RPC as well. The RPC stuff we're using is Pyro 4 for Python to Python stuff. There is a Java client, which I might use, depending on whether or not we move ops control to Python, but I'll probably stick with Java for the moment. And we're using Thrift, which is a cross-platform RPC, developed by Apache, I think, and that's used by the guy doing the correlator control stuff to manage the correlator processes. So here's some data. This is some actual output from the array during commissioning. So it was 105 out of the total of 128 tiles. And this type of picture has never been taken before. Nobody's ever seen the radio sky at this resolution at these frequencies. So you can see the Milky Way down here. You can see point sources, and these aren't stars, they're radio galaxies. And here, the bottom pictures show FM band a little bit higher than normal FM stations. So it's 108 to 118 megahertz. And you can see a pulsar on Fornax A, which is a radio galaxy. And the top pictures are the same area of sky at two different times, but looking in the FM band where FM radio stations transmit. You can see the same pulsar, the same format. You can see something else here, a little streak. That's actually the International Space Station. We're looking at Triple J and Nova and various local Western Australian and Australian FM radio stations reflected off the ISS. And you can see it moving through the sky. So that's the ISS moving through the sky. And we can see it in multiple frequencies. So across the bottom here we have frequency, and this is time. So you can see stations become easily visible and then disappear, and other stations aren't really visible and then suddenly appear. That's because the International Space Station has lots of complex flat surfaces, and the radio stations are scattered all over the country, and as each flat surface happens to give you a good angle, you pick up one station more brightly than another station. Well, you can quite clearly see individual radio stations reflected off the ISS. Yep.
So this is a problem for military satellites, right? Because, or are they just designing them with stealthy designs?
I don't know. It's pretty easy to spot. If you've got a rough idea where a satellite is, you can point an optical telescope at it and see it.
Any other anomalies like this that you can't match to known satellites?
We haven't spotted them yet.
Most of the military satellites are smaller.
Yeah. The ISS isn't.
This is like few nights or a meter per month. So there are all sorts of scatter work, and you're not going to see anything unless it's big. So we see, I think they looked for others, and they didn't find much else other than the ISS. But that's not to say there's not data in there. And there is a defense project both in the US and in Australia to use low frequency. I'm not even sure that they want to use FM radio, but they definitely want to use arrays like
Tracking space junk is a really big problem, and it's a known solution in that you can point an optical telescope at it. With the optical telescope, you have a really small patch of sky, so you need to know where the thing is roughly before you can see it in an optical telescope. This, if you have a breakup, if something smashed into a satellite, you can see the whole sky in one image. So if you could get better sensitivity, you could track space junk over the whole sky in real time instead of a single piece of space junk. So there is interest from the sort of space tracking people, but it's still a long way down the track.
In terms of resolution, Kevin mentioned this one, Parkes radio telescope, its entire field of view is 1 pixel in the map.
Yep.
So you get all of that one.
Yeah, every 8 seconds, this is actually, so that's 9 hours, but every 8 seconds you will get a lower sensitivity version of that coming out of your radio telescope, as opposed to a single pixel where you might point the Parkes radio telescope here for 9 hours and then move it next door and then point it there for another 9 hours, then move it next door and so on. It's the whole sky at once instead of pixel at a time. And this is kind of sums up the whole SKA project. This is Danny Jacobs from MIT in the US, sitting out in South Africa using, next to the paper low frequency radio telescope. And his laptop is connected via the internet to the MWA. He's actually observing on the MWA while in South Africa, and he's from MIT. So it's sort of a nice global picture of international collaboration. And that's it. Anybody got any more questions?
Yeah, so I've got a few questions actually, but I'll start with the first one. So for the dipole antennas, spider-like construction, how much of that is actually the active antenna?
Well, the whole of the metal spider.
Oh, So
Yep,
that's
it's insulated from the ground. It's sitting on a little plastic support, so it's not actually resting on the mesh. The mesh forms a ground plane to reflect signals back up, but all those spider arms are the actual antenna. The white cylinder inside just has the amplifiers.
Yeah.
The back of the shape gives you the broadband.
Right.
Well, you're getting instrument hole rate from all over the sky. So to get Stokes, you have to do quite a complex matrix, one matrix transformation that's direction dependent. So we do produce Stokes maps, all the maps generate that's done with a lot of processes.
Yep, up the back.
What kind of angular deviation can you get with the beamformer?
Very, very coarse pointing. So we've only got 31 steps on the delay, but our beam is huge. Our beam is, 20 degrees across? So you don't really need very fine pointing to be able to steer a beam that coarse. When you do the post-processing in the interferometry, you get an all-sky map. So you get pixels and an image that covers the entire sky, but you're most sensitive to a patch where the beam is physically pointed from the beamformer. So you're very sensitive to a patch of sky 20 degrees across, but you still get an all-sky image from the interferometry. So you just point where the maximum intensity, where the maximum sensitivity bit is. Often you want to point the maximum sensitivity bit not because you're particularly interested there, you want to point it away from the sun, and you want to point the side lobes away from the sun or bright galaxies or stuff like that. Because
I think in principle the beamformer can point almost anywhere on the research sweet spot where it's most sensitive. They're basically because they're using whole units of delay, aren't they? You can use some sort of
yes.
So, and that works out to be a couple of degrees. It's a function of elevation, but I think it's pretty much 1 or 2 degrees apart.
And you can't point right to the horizon either. There's kind of a scallop pattern like that defines where you can point. And that's defined by the maximum, no, it's defined by the maximum delay. But if you can't make the delays long enough to point all the way to the horizon diagonally, but you can north, south, east, west. Yep.
You have mentioned that you see reflections of RF signals from the Earth.
Yep.
Isn't the problem that you would be receiving actual RF signals?
Oh yes, yes. Yeah, there's several sets of, there's a bunch of military satellites that take out a couple of channels that just make it useless. There's Orbcom communication satellites that occasionally spike in another channel, but the majority of the bandwidth is pretty clean. When a plane goes right overhead, it's pretty much a write-off. But most of the time and most of the frequencies is really clean.
Yeah, so eventually you will know quite a lot of frequencies of
Yep.
lasers and lights. Yep. And how about Aurora and these, Aurora Australis?
I don't know. I wouldn't have expected it to be a problem that far north, but I don't really know. Do you know?
Because that's also
Never thought about it.
magnetic phenomenon.
Yeah, no, I never thought about it. Yep.
You talked about operational tiles. How do you know if a tile has failed, and how do you know if a receiver in tile has failed?
We can test the individual elements. We can test each dipole because in addition to setting the delays, we can also set an individual dipole off by simply turning it off so it doesn't come through. So we do what's called a short dipole test, where we step through and turn off all of the dipoles except for one, make sure we see the right spectral pattern from that tile that indicates that dipole is not returning a corrupted signal, it's actually signal from the sky, and that it's okay, and then we step on to the next one and so on. So we can test each dipole, and each tile we can actually look at individually. The actual output data has real data from each tile.
Okay, so a related question then. When you introduce a new tile, how do you calibrate the array? What do you use as a test signal?
I'm an optical astronomer, so I write the code. once it sort of leaves the analog side, I'm kind of lost. So
The way you calibrate an array, especially at low frequencies like this, especially one with a very large view, it's quite complicated. But the simplest way of doing it is trying to find a bright source in the sky that dominates the signal in that particular direction. Having some gain of the antenna so you can point the antenna at a bright radio galaxy. And all of the individual antennas are essentially seen. But they're seeing it so weakly you can't detect them in the visual antenna. But you form a set of correlation pairs. And each correlation pair should be seeing, if it's a true point source, should be seeing the same strength of correlation. And then you use that to weight each individual pair of antennas. You very rarely get an individual antenna calibration. It will be a true extractive operation. But you basically source of brightness and non-magnetic visibility. So all of the antennas are seeing the same strength in the sky, but they'll be demonstrating a different strength in the data set because they've got different gains and their performance. So you scale them relatively to an arbitrary. You just pick one, you think this is one I like, this we'll call this one, and make everyone a 6.
So do you brute force that, or what do you do it for?
So the whole process is a big linearly squared minimization operation with the gains of the individual antennas as the unknowns. So it runs through a loop called self-calibration, which has been around in radio astronomy for many years anyway, calibrating sort of low-end arrays, having a handful of arrays. And when you apply it to a lot of antennas, it gets a lot easier because you've got a lot. The number of unknowns you have is only going as the number of tiles, but the number of measurements you have is going as the number of tiles squared. So you get a hugely overdetermined unit square.
And that tells you where each of the tiles are to within a few millimeters, and it tells you the sensitivity of each tile and a whole bunch of other things.
Close enough to the first guess.
Yeah.
So you have to get close enough. You have to know your length of your cable. You have to know roughly the gains need to be roughly.
You need to know what's on the sky if you want to use it as a calibrator. Radio astronomy is very recursive. Optical astronomy, you take a picture, you see what's there. Radio astronomy, you need to know what's there to start your calibration process to produce a picture.
That's essentially the biggest problem, is that no one has really done this sort of experiment before. Ourselves with LOFAR and Northern Europe doing the same thing at the same time. So we don't really know what the sky looks like and those sorts of scale. So most of our calibration routines don't work because they assume that you've got a nice bright source, you're pointing a big fish at it, all you're seeing is this one radio galaxy. But with like a set of TV antennas in the field, you're seeing the whole sky almost